Yeah, as Harald already mentioned, this was a short talk for the last Unity meetup, and it's still a short introduction into compute data. So don't expect anything fancy, but this will be a series. So we will continue to make more compute shaders in the future, which more, I would say, advanced stuff. So this is like a beginner's introduction. My name is Gottfried, and I welcome you to this short introduction to compute shaders. So let's start with the definition of compute shaders and what they are. Basically, a compute shader is a program that runs on the GPU instead of the CPU. It can completely run independent of the rendering pipeline, but you can also use it to enhance stuff on the render pipeline. The big advantage of using compute shaders in comparison to the CPU is that you can run the algorithms in parallel on your GPU, which is then called GPGPU or general purpose GPU. So we are not using the GPU for rendering images, but to make calculations and do other stuff. But as I said, like you can also use it to accelerate parts of your rendering, mostly post-processing or simple other mathematical issues. One caveat is to use them efficiently, you should understand the GPU architecture and how parallel algorithms works in general and how you can exploit that on the GPU. Another good topic is like, because compute shaders are tight bound to DirectX, to see or to look more after direct compute, OpenGL compute, CUDA, or OpenCL. So they are all kind of hitting the same topic, but with different approaches. We have here for sure using the direct implementation of Unity and what Unity is presenting. So why do we use them? This is a nice, I think, a nice illustration. If you compare the pictures on the right, like the above would be a CPU that is like single processing stuff, whereas the bottom image renders stuff in parallel. So I think that's a nice visualization how to speed up things. The cannons are all the same power and all equally fast or slow, but if you have only one, you can only draw one pixel at a time, whereas if you have running something in parallel, you can make a bigger picture in one shot. So it's mostly for speeding up your calculations in simulation or procedural generation. You can also do pathfinding or do some advanced math. As I said, it's called general purpose GPU. So you're exploiting the GPU to make calculations that has nothing to do with graphics. We all live in the age of Bitcoin and cryptocurrencies, so this would be also like a purpose, a general purpose of the GPU. I don't know if they run in parallel, I have no clue. But this is like exploiting the GPU as a speed up for calculation that can, or that will be slower on the CPU because you don't have that much kernels. So another thing is for sure we offload processing power from the CPU to the GPU, so we can also use it for physics or other stuff, and then have more time on the CPU to do whatever we want. In Unity, the compute shaders are programmed in HLSL, so this comes directly from DirectX. You cannot use CG or other languages, so HLSL is here the only language of choice. But it's, I would say, not that much different from GLSL or CG from NVIDIA. It's yeah, kind of subset of C, which very easy syntax. So this is the first hand-on. How do we start with compute shaders? First, you have to define a compute shader. You have to create a compute shader. Then you make a script, assign a render texture to your compute shader, and then you can display the image. So for this, I make a live demo, and I hope I'm doing well. So the first is like we go to create shader and then to compute shader. I'll wait until the video is updated. So this would be our compute shader, and then I create a C# script. Okay, let's go to the slides. If you create a compute shader, this is normally what you get in the program. So this is more or less the standard code Unity gives you when you create a compute shader, which you see here. I will explain you in a short moment what this is about. I just have to, let me see, update the script accordingly. Okay, I cannot copy paste from here. That's a pity. Give me a second. So for sure, it's always the wrong screen. So I copy just the code. No, in the PDF, it's also not working. Why not? I tried it before, so it will work. Going back to Visual Studio. RGB, the kernel is kernel. And the first thing is like we have a CS main here, which is marked as pragma kernel CS main. So you can call the function whatever you want, but you have to mark it with pragma kernel so that Unity knows this is a kernel to compile and run. And afterwards, you can take its name and texture here inside. So this is the basic setup. We have here read-write texture where we can read and write to, which is our render texture that we assign to the kernel. And the most important thing is the CS main, which is running, and this NumThreads defines how many threads can run in parallel. I will maybe when we have time at the end of the talk go into detail about this NumThreads. Yeah, basically it defines in which dimension you want how many threads running in parallel. So at the moment we have a 2 by 2 by 1, which means in X and Y we have 8 threads running and 1 in the Z direction. Since we do nothing with 3D texture, the 2D version is sufficient. And then we go back to Unity.
There is in line 21 in the shader. You have a
extra bracket, I think. Yeah.
Yes.
Thank you. Yes, copy and paste. Thank you. I should do this more often. It's autocorrect on
mob programming.
Yeah, that's awesome. So I attach our script to hello. Because the game object is not selected. Okay, so in the script, yeah, maybe I should define say something about that. So I have 2 serialized fields. With one is the compute shader where I can assign the compute shader, and the other will be the render texture where when I create the render texture, can render texture. So drag dropping our compute shader into the program, hitting play. And we don't see anything, but if I click here into the render texture, we see the result of the compute shader. since this is quite tedious to do, there are for sure other things. And the first would be like, at the moment, I have hard-coded. The NumThreads will also always be hard-coded. But I also hard-coded how I dispatch the kernel, because I have a 265 to 265 texture and 8 kernels. I divided it by the width and height. I divided the width and height of the texture by these values of the kernels. So if I change the numbers here, we can make it direct. If I change the numbers here and run it again, you will see that we are now not processing all the complete texture. So these numbers correlate with each other, and you have either to do it manually, or as I will do it in the next example. So this should work again. Hitting run, going to the text, we have the same result again. To make it more easier for us programmers, we can pass variables into the compute shader, which I do with giving it the resolution, and then it can directly calculate the resolution based. No. It can then calculate the colors directly based on the resolution. So at the moment, our compute shader is just dividing by 15. So this means every 15 pixels we get a value from 0 to 1. This is why this pyramid shaping thingy is showing us. So I take now the resolution of the texture we have.
Sebastian is asking if you could demonstrate things a little bit slower.
Yeah, for sure. Sorry. So at the moment I do no magic here, so I just get maybe I should also explain what ID is. ID is the thing we get from the compute shader. So it's basically the ID of the NumThread and the pixel. And then in the resulting texture on the position of the pixel, I write back. And what I do now is, like, I know that my texture is running 256 pixel wide and 256 pixel high. In height, I can directly calculate, like, with the ID of the thread of the pixel, the value I want. So this is a very simple color grading program, so to speak. And as you see, I get a nice gradient from black to green and from black to red, and in both directions it combines to yellow. But what I can't do now is altering the dimension of the render texture, or I can say it's like 512, but then I have to go to the compute shader. I leave it by now. Let's see what's happened then. We should get a saturated image. So you see at the half of the width, we get just the yellow color because our pixels are running from 0 to 512, and I divide only by 256. So if I correct this here, and I hope you get the idea where I want to go. If I correct this here, then I get my full gradient from 0 to 1 in both directions again. So, and since this is very tedious, we can switch to the next slide. We can pass the resolution of the texture. So I can then have a value from 0 to 1 if I divide it by the texture. I hope this is clear. Let me save. Okay. So this is more or less the example we had. So, but okay. This should already have the resolution. Let me check. Resolution gets passed to the thing. Yeah. I think I have missed script missing. So here I can alter the resolution. Let me see if it's working. No. I'm confused now about my own code. Here. I didn't serialize the field. So let's serialize the field. Sorry, I wasn't close to that all before I started the meetup today. So now I can easily change the resolution without changing, let's say, the outcome on the render texture. I just can change how many pixels I want in the render texture. So if I want to make it smaller, now let's make it. We then get a smaller version of what we want to do. Then I prepared other scripts. Wait, let me see if I have some slides. So this was like about the resolution. So I passed through the resolution of the texture, and with the pixel ID divided by the resolution, I get a value between 0 and 1. And this is for the next upcoming Computators relevant to make it more or less independent of what the size the input texture is. Yeah, I have more scripts here prepared, but I didn't put them on the slides, which is not as good. Let's see. I will explain them shortly. So this is more or less now the same script, or it's the same Computator. It's not a sign. It's the same Computator, but now I directly put the result on the screen or to the camera, which is much easier than to run through, as you can imagine. So if I change the resolution of the texture again and run the script, I don't have to click on the render texture and directly see the image on the camera display. So what I did for that is, like, we have more or less the same setup. So we make a render texture. And let me see if I get them side by side. So I still create a render texture. I still set up the compute shader, but in the end, first of all, it's not start, but on render image, and then at the end I make a graphic split so that the render texture gets to the camera view. If Are there any questions concerning this, or shall I go into detail of that? This is more or less a basic Unity splitting operation. You get a source and destination render texture, and you can override it and make simple stuff. This is also if you make post-processing stuff the old way, the way you can go. So let me check. I should open the chat here too, so I see.
No, there are no questions. So the only difference is that it's triggered on render image and it
Exactly.
splits
So
the result.
Before I had like rendered texture exposed to the object, to the inspector view. Sorry, I did too much stuff in Unreal lately, so I have to come back to Unity again. So when I create the render texture, I can then I can attach this script too. I can then click on render texture and see the result. But with the splitting operation, I don't need that anymore. So I don't need to expose render texture. So this is completely private now, and I create the render texture on this render image, which is called once, and then the computer shader is invoked, set up, and dispatched, and the results from the render texture in the compute shader is then split onto. This is more or less the basic setup, and the next thing is like to introduce a little bit more interesting stuff. Is like putting time into our compute shader, and for that I have a script like I need a time. So I set up in the start what we did already, the render texture, the kernel. So the kernel in itself is just a number and depends on how many kernels you define in your compute shader. So you can have more kernels defined, and with the next function, whatever, you can define another kernel. So, and with that, you can have in one compute shader program multiple kernels. Let's call it maybe time and time. And nice exercise. And we need a float time.
Can I ask a question?
Yeah, for sure, anytime.
Yeah, as I can see now we have two different operations working on same fields. For example, target, it's addresses in these two directions. Two dimensions array. What's happened if both of those operations will execute it at same time with same object?
Since you make more or less the same calculation, nothing will happen. So if you have overlapping threads, they will calculate the same result. As you see, the mathematics I do is based on the pixel ID.
Mm-hmm.
So the result is the same, and you maybe waste GPU power because you calculate it, but from the side it will not do any harm.
Okay,
if the question relates to having different kernels,
mm-hmm.
then it's like on the dispatch. If I go back, just copy the thing here. If I go to dispatch, I now go to. I specifically say dispatch kernel number. So as you can see here, you say which kernel you want to execute. You cannot execute two kernels at the same time. If you want to execute kernel 1 and then kernel 2, you have to call them separately.
Okay.
So if you have multiple functions, or let's say multiple kernels, because you can have multiple functions. If you have multiple functions, you can only execute one kernel at a time, which is done by dispatch.
Sorry, Gottfried,
Yeah.
I missed the first part. What type of shader we are creating? This is a
At the moment, we just make this color gradient.
standard, standard
Yeah.
surface, or
We have a render texture. So in principle, we call for each pixel, we call this function. This is our kernel, and the kernel function is like into the render targets on pixel ID XY, we put this, let's say, color, this result.
okay.
And this is done in parallel by 8 by 8 threads on the GPU. Maybe if it's not clear what I'm talking about, maybe rephrase the question.
No, actually, I was talking about what type of shader we create on Unity. What type?
This is called the compute shader. So this
The
program,
compute shader. Okay, got it.
this program that runs is called a compute shader. So it's not like a graphics normal shader,
Yeah, exactly.
where you have to calculate colors. Yeah.
Thank you.
Okay, be welcome. I hope I set up everything correctly. So I said kernel 1, and yeah. So yeah, in start we initialize everything, make a first dispatch, and then in the update we I had fine here, so I don't need to multiply it here. And in the update we dispatch again our shader, so it now gets a running time into the shader. So I removed this just time. I disabled these scripts and run it. Maybe too fast. Okay, I made a mistake. Time has not. I make it stupid and easy. Sorry. I will not make 2 kernels at the moment. Let's see, where does this lead to? Resolution. I didn't apply the compute shader. Okay. So let's revert that again. Maybe it was all correct. I take kernel 1. Okay. Let's try it again.
Do you need to serialize the render texture?
No. I come quickly back to that.
Okay.
Now it's running. Index is not set. Okay. Sorry to confuse you now. As you can see, I only have serialized compute shader resolution on time scale, and the render texture is completely private because it's anyhow only used internally, and we used it in the first example only to get access to the render texture. The result of the compute shader was.
I missed the graphic split in the bottom.
Yeah, sorry. So 1 second is maybe much too high. So now I downscale the time passing by, and the more time it passes, the more it should get yellow. And this is maybe too much to wait. Yeah. Yeah. Oh, that's that. But having now like a value between 0 and 1, we can also do like what, as I said in the beginning, having mathematical operations. So the next thing we will look at is a simple, very simple randomized function. It's not 100% perfect, but it's working. So it's, as we always know in computers, there's no really real randomization possible, but this is like a pseudo random number generator. And if I hit start, I hope my internet connection is fast enough to catch up the updates. It's super laggy. Okay, you see a picture. So on my screen it's flickering. I see that my mouse cursor is super slow. Let me check if I no. So as you see, if you get the updates, there are different, or this is like color noise. And if I go back to the compute shader, it looks like now it tries to buffer everything I have done. Yeah. I have defined, so let's go to the, I've defined a random number, which is kind of a fancy function to generate random values on the GPU. So this is my rand function, and I call it then from my kernel. And this is dependent on the positions I'm on. So I generate different different random numbers for each of the 3 RGB values. And from the script, I don't think I need some. Yeah, from the script, it's always the same. Like we search for the randomized kernel. I give him the resolution and the target for the render textures, and then execute. So, and since we can do any calculations, we can also use mathematical functions. I show you in the next thing, like I have multiple mathematical functions which I overlay and compute like colors out of it. So I will jump directly into the compute shader. So the center function is just giving a nice fall off around the point. And then I can enhance this with sinus and cosinus values. And at the end, I make a what do you say, an exponential square function, so you get a nice peak. And wait, I don't see my own video. So, you get a nice peak, and then in the kernel functions, I call those peak 3 times, and with time, I'm altering the positions of the peaks. So in the end, I'm just calculating 3 peaks that are randomly or quite randomly running around the screen. And if I go back to Unity, go to my functions thingy and hit run, let's see how fast it is. So yeah, kind of updates it. You see these 3 peaks interact and overlay, and yeah, that's more or less this little demo. I will try to make a GitHub repository and put all the code there so you can try it out yourself.
Yes, that would be awesome.
Yeah.
Thank you.
Maybe, yes. So going back to the slides. So this is like, as you have seen now, you can do anything in a compute shader and calculate stuff, put it into a render texture, and then use the value wherever you want. At the moment, I used only an RGB render texture, but you can use different render textures and by that passing different values back to whatever you want to have. Yeah, what I already said, like compute shaders are related to shaders, but are different in the sense of how you program them, because you have a kernel, and the kernel can then call other functions. So this would be like in a compute shader, we normally have a pixel shader and a fragment shader, maybe a geometry shader, but here you have only the kernel, which you can distribute to different threads. And they are then computed into your compute buffer or render texture. And with that ability, you can transfer data between the GPU and CPU. You can take load off the CPU. And yeah, in the end, you can put any structs, or you can define structs and put structs as arrays to the compute shader and do fancy stuff with that. I will cover this in the next, hopefully next meetup. As I said, I want to make this a little bit a small series, like maybe 2 or 3 parts, and then we dig into compute shaders. So, oops, that's all from my side now. If you have any more questions, feel free to ask.
Can you share some interesting tasks from your experience that you was using compute shaders?
Sorry, come again?
Can you share with us some interesting tasks which you was resolved by compute shader?
If I have, I don't get the whole question, sorry. If I have,
I think it's about a use case. Do you use compute shaders in one of your projects?
yes, I use compute shaders. Let's say compute shaders, no, but compute buffers to get arbitrary data to shaders. So I have a big struct and fill it with data. So I have an area of a struct, fill it with data, and then can use it in a shader. Like what I want to do in the series is maybe altering positions of objects via compute shader and stuff like that. So I will come up with maybe a useful case for compute shaders, but at the moment I have nothing. I have nothing to show you. If this hopefully answers your question.
You
Yeah,
showed some simulations. Do you have in the beginning? Have you looked into them by just maybe coincidentally? Do you know how they use compute shaders?
Yeah, the only thing I know of, like as you know, there are a lot of how do you say, on supercomputers, you do a lot of stuff like simulating galaxies and stuff like that. So this would be an example. The most things I stumbled upon was like doing fancy particle effects or so. Yeah, as I said, you can do it for mathematical reasons, and where you want to run small algorithms in parallel. Because they're super fast on the GPU. Yeah. So personally, I haven't done anything yet with compute shaders, but I would like to, especially with particle effects and particle effects not like on 2D sprites, but really on 3D objects, because you can use GPU instancing and then use hopefully the positions calculated by compute shader for doing stuff. Another example would be maybe making procedural terrain altering in real time or something like that. So I think there are implementations of marching cubes on the compute shader, but I'm not sure, to be honest.
Thanks. Any other questions?
Yeah, I have one question. Can you share this code maybe in some
Yeah.
repository?
We
Thank
will set up a GitHub and then post it in the meetup.
Nice.
And yeah.
Thank you.
So the goal is also to collect a little bit of the stuff for future reference, I would say. Yeah.
More questions, please.
Do we have some limitations for compute shaders?
The limitation on the one side is how big you make your textures. I don't know how much it is, or if there's a restriction. I think it's either 4 or 8K. Maybe it's bigger now. The threads in parallel is something between, or is limited to 1024, and threads in groups are something, depending on the hardware, between 32 and 64. So yeah, maybe I can go a little bit, have an insight to the num thingy here. So this defines a group of threads that are running in parallel, and I think on AMD you have 64, on NVIDIA you have 32. So you can make like 4 by 4 by 4. This would be 64. You can run 64 in parallel, and from the hardware perspective, you have, depending on how much single kernels you have, kernels not, how do you say, the missing
Threads.
word. Threads, no, not threads, like hardware, the CPU thingy.
It's like a job for a GPU.
Yeah, exactly. You need, like, I don't know how it's called on hardware. The latest was like 768 on a GeForce whatever, 789. Let me Google it.
No, it's I understand. Another question. So if we need to optimize some compute shaders for any specific platform, we just need to create new one, define these numbers, and just reuse other one.
Exactly. So also what people post in the forums, like with these numbers, you can tweak around, but it's very, very hardware related. So it might be fast on your hardware, but not so fast on others' hardware. So the common sense is like using 8 by 8, so 64 threads. You can for sure go 32 by 32. Let's just check this out. I don't think that there is any restrictions on the numbers. So I'm not sure, sorry. I haven't seen if you have seen my update with what I did, because I was blocking myself on the other machine. So in the compute shader, I put here wait, I have to wait. So I changed the NumThreads to 32 by 32. And in the dispatcher, I set the resolution to divided by 32 by 32. And let's see what's happening. I think it should give us the same result. So I hit play. And as you see, it still runs on my machine. I don't see a difference. Sorry, because the video is lagging. You don't see it fluently. So you can experiment with these numbers, but it's not guaranteed that it's not slowing down hardware if you make the numbers too big, so to say. So a common sense is something in the range of 64 with current hardwares.
Cool. Thanks. I would also have a question. Do you always have to use a render texture with a compute shader, or can you use a compute shader in a different way as well?
I don't know if you can directly use a compute buffer, but since a compute buffer is more or less a one-dimensional array of structs, data, and that's also like in a buffer. So like from the hardware, a buffer is always the same. You define only the layout. So a computer buffer defines a layout by a struct as an array, versus a render texture gives you an array defined by a 2x2 format, and then the render texture format, which you can choose off. I have not dig deep enough to know if you could use any arbitrary return values. I think you're limited to render textures and render texture formats.
Okay. At least that's probably the most common.
Yeah.
Okay.
But yeah, but to be honest, I don't know. I don't know if it's yeah. If it's
Sebastian is asking maybe a general question about shaders. Are you able to share shader functions and import them in different projects? And is there any packaging system, like a package manager or something?
I don't know if I completely understand the question. So if you want to share shaders in different projects, you can either do it with a subversion system like a versioning system like Git or something, and make either submodules and reuse them in different projects. If you want to have it as a package, you maybe use one of the packaging tool online. I have never played with it.
Could you use a asset bundle?
That should be working, yes. But yeah, asset bundle shader code, you have to do it per platform.
So asset bundles are a way of sharing materials, but also scripts in Unity. With scripts, it can be tricky, but materials usually should work.
Materials and shaders are working. They are transformed in the specific platform. Code you can't share. So code you have to make an update of your program if you want to share.
So you have to create a bundle for Windows and Mac separately, Android or iOS.
Exactly. Yeah.
Thanks, Sebastian. Any other question? Okay, I think you answered everything, Gottfried. Thanks a lot for the presentation and the demo. I'm looking forward to the continuation of the series.
Yeah, me too.
Sounds like it's a motivation for you to dig deeper
Yes,
in Computators.
That's true.
Which kind of already brings us to the next topic. Let me stop the recording now.